Hello, my name is Casper Abassi, and today I'll be showing you video presentation 2 for fluid dynamics. The question tells us water is pumped from a large tank shown in the diagram below. The entrance to the pipe section is sharp-edged, and the cast iron pipe has a total length of 2 meters. Flow being observed to be fully turbulent, the relationship between volumetric flow rate and actual head rise is provided below. We're asked to find the volumetric flow rate for the system and show that the observation of fully turbulent flow was correct. In addition to being asked that if the pump is 70% efficient, how much power must be supplied to the pump? So let's go ahead and write down our given parameters here. We know it's cast iron. We know our length is 2. We know it's sharp-edged. So these are going to reveal to us through our textbook, when we look it up, that we have an epsilon value 0.26 times 10 to the negative 3 and a KL value of 0.5. Our diameter is 0.07. Our Z height is 6 meters. This is given from our diagram. And we know HP equals 20 minus 20,000, 2,000 Q squared. Okay. Now we're going to write our Bernoulli equation. And so this Bernoulli equation is going to have our HP and our head loss in there, and that's going to help us find our volumetric flow rate. So right off the bat, we can eliminate P1 and P2 because these are both atmospheric pressures, and those are going to go away. Z2 is 0, and V1 is 0. So this is going to give us the equation. Here. And we know our HP in terms of Q, which we can set in terms of V and solve for V if we find our head loss. So head loss equals head loss major plus head loss minor. Major head loss equals friction factor times length over distance, V2 over 2G. The way we're going to find this is our epsilon over D value, and that's going to be our relative roughness, which we can then use with our Moody diagram to find our friction factor. Okay, so when we look at our Moody diagram, this is going to correspond to a friction factor of 0.027. So we can go ahead and plug that in. Length over diameter. And that's going to be 0.77. And that's our major. Then we have head loss minor, which is KL V2 over 2G. So plugging that in, we know our KL value is 0.5, so we have simply 0.5 V2 over 2G. And when we add these together, we get our head loss. So that's 0.77 V squared over 2G plus 0.5 V squared over 2G. That gives us 1.27. All right, now we have our head loss. We can plug that in and plug in our other known values. So these are all given values from up here that we defined earlier. Now we know our area is pi over 4 d squared, which is 0.0038, and we know Q equals V times area, so then we know that Q is really 0.038 V. And we can plug that in here. This is actually going to be an addition of 2.27 V squared over 2G minus 6. Now we have our entire equation in terms of V, and that's going to help us out. If we find V, we can find Q, which is what we're looking for. Okay, so a little rearranging here. Minus 26. This is going to be So this gives us a velocity of 17.3 meters per second. Now we can plug that in. And if we plug in velocity times this value right here, we're going to get 0.065 meters cubed per second for our RQ. And this solves part A of the problem. Next, part B. We know that if we have a Reynolds number of over 4,000, then we have a fully turbulent flow. So what we want to do is we want to find what our Reynolds number would be with our Reynolds number equation, and we know our velocity now. And this kinematic velocity can be searched in the textbook as well. And it's 17.3, this is 0.07. This is going to give us a value of a value certainly larger than 4,000. So this shows us that our fluid is fully turbulent. That's part B. Part C, we're asked for the power supplied, W dot, when we're at 70% efficiency, and that is defined as, I believe, rho G, our HP value times Q over efficiency. We know HP is in terms of Q, which we have. 0.065, 0.065 squared. And that gives us an HP value of 11.55. So when we plug this all in, we have rho times gravity times 11.5 times Q over our efficiency, which is 70%. And that gives us 10,500 watts, or 10.5 kilowatts. And that concludes video presentation 2. I hope you enjoyed, and have a great rest of your day.